so let's jump into decision trees now. We're going to go over kind of the basics of what decision trees are. We're going to talk about how we train classification trees, at least. Then I'll talk about interpreting predictions and how we, why these are kind of making a comeback, especially because they're a little bit more sort of understandable in their predictions in some sense than other models. Then I'll kind of switch gears actually entirely and go the full opposite direction, which is uninterpretable models again, which use trees. And I'm mainly doing this is, of course, the boosting side of things. And I want to do this mainly just because I at least want to mention boosting briefly in this class. It actually ends up being the algorithm that wins things like Kaggle contests the most often. And so we should actually just sort of at least describe it in a few slides what it is. And finally, I'll just have a few code examples at the end, but I might not actually get to this. You can just look up in the slides if we don't get to that part. OK, so let's talk about decision trees to start off with. So decision trees, again, they're some of the most ubiquitous algorithms in data science, mainly in combination with algorithms like boosting, so this actually combines many trees. And actually, as I was saying before, when you use things like boosting, a lot of the advantages of decision trees, like their interpretability, actually kind of go out the window. They're no longer really considered interpretable models. But they are certainly very important, both on their own in terms of sort of understanding predictions, and when combined with more powerful methods like boosting or ensemble methods in general. And as I was saying before, the majority of Kaggle contests, it's maybe not quite true anymore. I think they're aiming for things now that need a little bit more deep learning, which we'll cover actually next time. But I think there's a very large percentage, and sort of certainly historically, boosting is still sort of way ahead in terms of winning these contests. Now, as I've also been emphasizing a lot in this course, Kaggle contests are not data science, right? This is just sort of one, the top possible machine learning performance is just one slice out of the entire data science stack. But it's still a useful tool to have. And they are sort of one of these canonical examples of an understandable or interpretable ML algorithm. So what are decision trees? They actually were one of the first machine learning algorithms. Historically, they were actually one of they're sort of a very kind of intuitive way of thinking about machine learning. And they really were one of the first machine learning algorithms. Kind of when machine learning was coming up as a field first and was being developed as a field, they were one of these first methodologies. And the basic idea is we're going to make classification or regression predictions. You can actually use them both for classification or prediction. It depends what your predictions are at the leaf nodes. But we're basically going to do this by tracing through a tree and making a constant prediction when we hit a leaf node here. So I'll go through this example in some detail, but you can already kind of see we do things like say, is x1 bigger than 2? If it is, you go, say, this way. If it's not, you go this way. That's arbitrary which way you go, but say no is that way. This is yes. Sorry, yes is this way, no is this way. Then is x2, second coordinate bigger than 2? If yes, you predict this. If no, you predict that, and et cetera. You sort of take this chain of decisions that you make based upon testing, in each case, individual variables and comparing them to a single threshold in the internal nodes here. So let me actually describe that in a little bit more detail, because I think seeing this graphically can actually help. So the way to think about this is you should think about this in terms of taking your input space, your x space, and we're still considering x as a continuous valued vector in Rn, though oftentimes these are also applied to discrete input spaces. And you can think about it in terms of partitioning the space in terms of what wind up being equivalent to axis-aligned boundaries. So here's what I mean by that. So when we start off in our tree, we start at the root node here. Okay? And we compare our prediction, our data point, to some threshold, which in this case is 2. So if we see if for this example, is x1, the first coordinate of x, bigger or less than 2? And that's the way to think about this. This is sort of a slice in this space, right? Because all examples that are on this side are going to go down the right portion of this, and all examples on this side are going to go down the left portion of that, right? So you're dividing up your sample, your input space into these different regions. So now suppose you are in fact less than 2, so you're on this half of the space. Now you go down one more level, and now I partition again this space, right? So now I look to see if my second coordinate x2 is greater or less than 2. And in this case, say maybe it is greater than 2. That would be this region here, corresponding to this region here, where I split the space here. And so this whole region there would have a single value of the hypothesis function, given here just by predicting the value 0.7. This could be a regression tree, or this could be probabilities too. Now what's important to know here is that these splits are all they're all hierarchical, right? So if you go down the other branch, you don't necessarily make the same checks at all, right? You can look at different values here. I guess this one does happen to look at x2 in both cases, but you can look at other values, other nodes to split on, depending on, I mean, there's only 2 here, so it's not very useful. But depending on, what seems most relevant in this branch of the tree, you can make look at a different variable, make decisions based upon that. Okay, so at each branch, we're kind of dividing the space and determining how to make our predictions, looking at one variable at each node, right? And that's a decision tree. So this seems very different in some sense than what we've done before, right? Because almost all our predictions before use things like linear models, or models that were linear in some arbitrary nonlinear features of the data, but still this kind of intuitive form of maybe it's like a the product of some parameters times a feature vector, right? And this seems very different. So this seems like we're much more discrete here. We're much more kind of, how do we do things like gradient descent on this? You actually can't do gradient descent here because this is all a discrete space, and these are sort of hard thresholds. At least you can, but it's sort of tricky to do if you want to go that route. So the question then is, how do we actually train these trees, a hypothesis function like this, to actually get good classification performance or good regression performance? That's what we're going to spend most of the next bit of this lecture talking about. But first of all, does this sort of general form of this hypothesis function, really is what it is, make sense to everyone? Okay, so let's go about and talk about now how we train decision trees. And here, the nice thing is that, again, we're back kind of in the supervised learning realm, though we could apply the same methodology and to a large extent in unsupervised learning too. But what we're going to do is we're going to think about these same 3 elements of a machine learning algorithm. I know I'm sort of sounding like a broken record here, but this is sort of the this is the formula for how you apply how you develop any kind of machine learning algorithm. So to determine how we sort of specify a full decision tree algorithm, we need to specify 3 things, right? We need to specify, first of all, what's the hypothesis function? That is going to be our tree. So that one's actually pretty easy. I think we've already talked about that. Decision tree. And really here, our parameters theta, we're still going to call them theta, but theta in this case is actually kind of complex, right? It's kind of the set of all variables you split on and thresholds you split at in the whole tree. So you think of theta. We're not going to take gradients in the same way, so it's a little bit less important here, but you can think of theta as just kind of like a vector that describes the form of the tree, right? You actually can be very formal there. You can sort of say it's a list of indices that describe the split features, and then it's also a list of thresholds that describe where you split at those, but we're just going to think of it, as kind of the structure of the tree here. So then the next question, of course, is what's the loss function that we use? And here I'm actually going to now focus on the case of classification. In particular, I'm going to think about binary classification, where y is going to be binary valued. And we're actually, just for sort of ease of use here, I'm going to adopt the notation that we use a little bit more like in naive Bayes rather than the +1, -1. I'm going to adopt a slightly different sort of notation that we use more like in naive Bayes. And so I'm going to think of y's here as being binary valued in 0 or 1. Again, it's obviously very easy to map between that and the -1, +1 we use kind of for convenience of other loss functions, but this is just going to be our setting here. And we're going to think of our probability, in any given region, rather, of the tree. We're going to think of our loss function being kind of like the likelihood of a Bernoulli random variable. Okay, so what I mean by that is we're going to sort of assume that the probability of y, given our hypothesis function, this is, again, at some individual leaf. So our hypothesis function here is going to be just the prediction, basically between 0 and 1, of the probability that that value takes on the value 1. Right? So you can think of our hypothesis function kind of in this, I kind of was alluding to it before here in this example where I had all these things being numbers between 0 and 1. This is kind of like the Bernoulli parameter of a distribution where you're just sort of saying, okay, how likely is that thing to take on the value 1 or not? All right, that's going to be our predictions. That's how we're going to interpret our predictions at these leaf nodes. And in that context, the probability of this taking on this value, given this thing, right, is just going to be our normal sort of Bernoulli probability here. It's just this parameter to the y times 1 minus this parameter to the 1 minus y. Okay, and that's going to be our sort of the way we interpret this. And then our loss function is just going to be the probability, or the log probability, of this, you know, of the observed value given our hypothesis. And actually, we're going to think again in terms of the of the loss, not in terms of, you know, maximizing probability. So we're actually going to take the negative log likelihood as our loss function. Okay, so the loss function here between our hypothesis and y, and again, I'm being a little bit sort of I'm using notation a little bit here because they actually are, again, this is sort of our prediction in one region of the space. This is equal to the negative log probability of y given our hypothesis. This is, again, was sort of the standard thing we did to connect machine learning methods to probabilistic methods, which in this case, you know, this would just be negative y log h theta x minus 1 minus y log 1 minus h theta x. Okay, so that's our loss. This is our loss function, and this just encodes the log probability of our observed variable given our prediction. Okay, so that's our loss function. And by the way, if we were to use a regression setting instead, our loss function would just be the squared error or something like that. So this is, again, kind of actually the standard loss for, or standard probabilistic loss for binary random variables. But we could just as easily do things like squared loss for continuous random variables, stuff like that. Okay, so now the big question, of course, is how do we minimize this loss function, which again is our prediction, difference between our prediction and the actual output here. And again, I should have clarified here a little bit. So remember, I mean, our prediction here is sort of is a constant prediction at whatever region we are actually end up in, but it does imply, you know, we are in different possible regions depending on our actual example. So this is, you know, this h theta of x is sort of is this function here. And we suffer loss depending on, you know, the actual value of y and then the values we predict of this hypothesis function. So the question, of course, then is how do we minimize our sum of losses over our entire data set, right? So this is the third ingredient. So this is this is sort of part 2. This is the loss function, and part 3 was that we want to minimize over theta, which is now encodes our entire tree structure, the sum from I equals 1 to m of the loss between our hypothesis function evaluated at the ith example and yi. Okay, so it's just like every other machine learning algorithm, but the difference here is that this doesn't seem so easy anymore. Right? So the key challenge here is that unlike models we considered previously, even when we didn't apply gradient descent, right? Even when things like recommender systems we actually use some other algorithm, or in least squares where we use a, you know, closed form solution, there's no even notion of gradients here, right? Because decision trees and kind of the theta that we've kind of defined here is not like a continuous parameter like it is in other cases, right? It's just sort of the structure of this discrete tree. And then the values that we sort of predict at the leaf nodes, and also maybe the values that we have at internal nodes in the tree, which are our thresholds. And so it's not really obvious how we go about optimizing the tree to minimize this loss function here. Okay? And to make matters worse, the space of all possible trees is really big. It's actually 2 to the 2 to the n, because you can choose, you know, however you want to structure the tree and order your nodes within that tree. So it's actually a huge space of possible decision trees, meaning that, you know, if we have 7 input dimensions, there are some huge number, which we could never actually search, of all possible trees over our data. Okay, so this is really a space, and I think that actually even includes if we only have one split per level or something like this, right? So if you can go down as deep as you want, it's actually you can't even bound that. There's an infinite number of possible trees if you can keep splitting on the same node again and again. So we can't really do something like, we can't do gradient descent because we don't have gradients. We can't do sort of exhaustive search because there are just too many possible tree structures to ever search over. And so what we're going to do is we're going to use a greedy element, let's sort of layer by layer approach in the tree. Okay, so we're going to build our tree to iteratively minimize the loss node by this loss exactly, node by node. Okay, so let me describe how that works now. So, but the overall, are there any questions on sort of the overall picture of how we're going to do this? We're going to it's a greedy sort of element by element construction of this tree in order to minimize this function right here, to minimize the sum of losses on our data set. Any questions on that? All right, so I'll try to go a little bit slowly to kind of cover this because this is going to be the most kind of technical part of this lecture here. Okay, so I want to start by considering what we do in a single leaf of the tree. Right? And this is actually kind of obvious because it's just Bernoulli random variable predictions here. But I'm going to let X here be a set of all examples that reach a certain leaf. So all examples that reach a leaf. Okay? So, if I have, and again, I keep switching back and forth here, but if I have this example here, where you split the tree in this way and you end up here, X for this node here would be all the examples that fall into this region right here. Okay, so that's all I mean by X here. Okay, so then the question is, what should I predict? What should my prediction be at this region? Okay, if I want to minimize the loss in this region, well, again, this is sort of maybe in some sense obvious, but what I do is I look at the number of positive and negative examples that are in that region, right? So if I have some region in my state space, I guess I'll just draw this here because I keep going back to it. With something like this, right? So I had this H2, I think I called it. And so say I have some positive and some negative examples in this region, right? Some set of those. The question is, what should my prediction, if I were to make, a constant prediction in this setting, or in this region here, what should I predict? What we want to do is we want to minimize, and again I'll just say like minimize here over H because it's just a scalar value. So this is sort of a scalar, and really it's in 0 and 1 because I have to make a prediction between 0 and 1 to minimize my loss. So it's minimize the sum over all x, y in this set here of the loss between H and Y. Now, importantly, X isn't included here because X is only defined in terms of the examples that lie in that region. For the single loss function there, I'm not making any predictions based upon X. I'm just making a single constant prediction here. All right, and this is going to be equal to, I won't write it here, but this is going to be equal to just the proportion of positive examples here times log H minus the proportion of negative examples times log of 1 minus H. Now this is exactly actually just our coin flip example. Is what it really boils down to for Bernoulli random variable, right? This is just sort of saying, look, if in this region I basically flip a coin, the heads are my positive examples, the tails are my negative examples. What should I do to minimize the loss? Well, I pick my H here. What this implies is that H should just be equal to the number of positive examples, which I'll call X plus, over the number of total examples there. Okay, so this is just, again, I sort of took a while to get here, but this is just a matter of the exact same principle we use for maximum likelihood for Bernoulli random variable. It does happen to minimize that funny log likelihood there, but really it's just the obvious thing of, look, if I want to form my best estimate in a region, I just look at the number of positive examples divided by the number of total examples. That's my estimate of the probability that an example in that region is positive. And that's the one that minimizes this loss function exactly. Okay, so that's sort of the first point, is that if I want to predict something in this region, I should just look at the number of examples that are there and predict the proportion of positive examples over the total number of examples that are there. That's again to minimize my negative log probability as my loss function. Okay, so now is sort of the actual interesting part. So now the question says, suppose I have some region. Okay, so this is my region here. And I have a bunch of positive and negative examples in this region. And now I want to split this region on some new feature, xj. So in this case, if it's 2D, maybe I'm either forming a split like this or a split like this. Right? Now, importantly, and I do this sort of to intend this, you can't do a diagonal split, remember, because you're only looking at a single attribute and splitting based upon that. And so your splits are always axis aligned with a single feature. This is an important characteristic of decision trees. So yeah, I can do this split or that split. And, in both cases, they sort of seem like they're good because they still sort of separate this class. This whole region starts off with 3 of each of these, whereas this breakdown, in this half here, there'd be 2 and 1. This half there would be 2 and 1, and vice versa. So the idea here is that if this is my set X, right? This is my set X. What I would then do when I split on some new feature, xj, is that I would somehow be dividing my existing set into 2 new sets. And I'll call this, I'll say that this way goes with the case of xj being equal to 0. Let's assume that, actually, this is a bad picture now because I'm assuming here that xj is actually binary. But we could also do this, xj being bigger than some threshold or less than some threshold. Doesn't actually matter. You actually use the same technique for continuous or discrete random variables here. Or xj equal to 1. This would define 2 new sets here, right? And I'll call this, x1, and here x2. Or sorry, I'll call this one x0, this one x1. Okay? So now the question is, so now I've divided my region into 2 smaller regions. And if I want to predict what the value should be in those smaller regions, of course, I just do the same thing, right? I just look at the proportion of positive examples in that smaller region, and that's my prediction there. Look at the proportion of smaller things. In this example, that's my region there. So in this case here, of course, this, and again, with a little bit of looseness here because I'm sort of drawing this in 2D continuous space, whereas I'm drawing this in binary space for the actual example here. But our whole prediction here, if this first thing which is x, this would sort of imply that h in this whole x would have been 1/2 because I have 3 examples that are positive, 3 that are negative. But here, h1 would be, I guess I had 2 negative and 1 positive, so that would be 1/3. Say I'm sort of showing this split here. To this side and that side. And this one would be h0. And this one would be h1, which would be 2/3, right? Because I have 2 examples there. Okay? So again, all I'm going to do, I'm just going to break down this region however I want to. I'm just sort of evaluating possible candidate ways to split it now. I break it down, and of course, I'm going to just assign the obvious solution to the 2 subregions also. Okay, so now here's sort of the key question. The key question is, when I do this, how much am I reducing my overall loss? Okay, so when I started, I suffered some loss L. And the loss I suffered actually, I think I had this here, the loss I suffered is actually equal to, if you pick this value, and it should, this is just this thing pair, and then you simplify this a little bit. But what you get is that you get basically the loss you suffer originally is equal to negative h log h minus 1 minus h log 1 minus h. Okay, that's just what happens when I plug in this answer here into this equation, because of course this is h, and this is of course 1 minus h, because this is the number of negative examples there. So all I do is I just basically plug in my my solution to get the loss I suffer. Okay, so now if I split according to this, all I'm doing is I'm now saying, okay, I'm not going to suffer this loss anymore because I've now divided my region here. I'm instead going to suffer two other losses. I'm going to suffer for this first region here, I'm going to suffer L0, which is negative h0 log h0 minus 1 minus h0 log minus h0. And then I'm also going to suffer loss for the second region here, which is equal to negative h1 log h1 minus 1 minus h1 log 1 minus h1. Okay? And that's the new loss I'm going to suffer. Okay? So what really I'm doing here when I do this is I'm decreasing my loss by my old one minus my two new ones, right? So I've lowered my loss by this amount. Okay, and this is a quantity here called the information gain. Okay, and so all the decision tree algorithm does, and this is sort of the standard way decision tree algorithms are trained, is that they just will always look sort of on a node-by-node basis. They'll expand this in a greedy manner. And for all leaf nodes, they will evaluate the information gain, the quantity you will gain if you split on every single possible feature you can split on. So for all leaf nodes and for all features they could split on, they evaluate the information gain. That's how much you would decrease your loss if you split on that feature at that leaf node. Okay, so you've made it not a constant prediction anymore, but now actually had it broken down to two more possible predictions. All right, and once you've done this, you just pick the leaf node that minimizes the loss the most. In other words, the leaf node with the largest information gain. Okay? And that's it, actually. All right, so I'm just proceeding, and maybe you can do things like run cross-validation to determine when you should stop, because if you keep going, you might build too big of a tree that just overfits. So you might want to use cross-validation, something like that, to figure out when to stop. Or maybe you actually just sort of specify, I'm only going to have at most 50 nodes in this tree. I'm just going to build the first 50 nodes in the tree and then stop. Is there a question up there? Yeah. Yeah, so the question is how do you determine the split of the features? So if features are discrete, it's pretty easy, right? You just split on all possible values they can have. Okay? So actually, I'm going to talk about continuous features in a second. Maybe I should do that first, actually. So let's talk about continuous features first. So the case I had before was the case of discrete features, right? Where you could just say, so if xj is binary valued, you know how to split it, right? You split it 0 or 1. If it has 3 values, similarly, you just split into 3 different categories. It's not a binary tree then anymore, but it's like it has 3 branches in this tree. You split it into 0, 1, or 2. You can also do things like use a one-hot encoding of multi-way features. So you could have a feature that says, is this feature equal to 2 or not? And split on that as a binary feature. Okay, but what if, on the other hand, they are actually continuous features? What do you do then? Right? So it's actually very interesting what you do here. And it's actually a very sort of clever trick you can do. So the interesting thing about this is that we're going to split our features basically by thresholding comparisons, right? So saying, is this feature more or less than a certain amount? Okay, so is it is this feature xj, which is a continuous feature, is it greater than 100 or less than 100? And all our splits are going to be kind of like that. So the way that we actually figure out how to do the split for continuous features is that we look at a sorted version of this feature over our whole data set. Okay, so we're going to take our xj feature, and I'm writing this here because it's sort of like weird, superscript notation says I to the 1. What this denotes here is this denotes a sorted version of all my features. So I'm going to take all my features of this particular feature, again, in my sort of set X here that belongs to this node, and I'm going to sort them all. Of course, by the way, you pre-sort them in practice. You don't sort them every time anew. But I have them all sorted. And I'm going to look for every possible kind of breakpoint where I could split my features. I can look kind of at this half of the space as one new split, and this half of the space as the other new split. Okay, and so I can treat kind of this as my new x0 region. This is my x1 region. Then I can just move that split point over 1. Think about this now as my x0 region. This is my x1 region, etc. Okay, so I can think of in a sorted version. So for real value features, the short story is in a sorted version of your list, you actually consider all possible breakpoints you could have of this feature lying either below or above this point. Now the cool thing actually is that this is actually quite easy to compute. It's very easy to compute kind of the best possible split only in linear time over this number of features here by using a trick that depends on cumulative sums. So it actually does not end up even costing that much to do this. I won't cover that. That's still implementation detail. But the point is that actually it's not that expensive to even compute this. So you can basically get at the same cost of doing the discrete version of just having your splits. You can actually, as long as you pre-sort your features, you can actually have all possible splits and find the best out of all possible splits. So that's how you deal with continuous features. Yeah?
So for example, if your smallest value is like 2 and the second smallest is 3, like where do you split on? Do you split on like 2.1, 2.2?
So the question was, if you have if this is 2 and this is 3, what's that split value? Let's just say 2.5. Doesn't really matter. I mean, what you can honestly do is you can just have a rule that says it's less than or equal to the bigger one, maybe, or something like that. Or sorry, greater than or equal to the bigger one. So just split, right below that on exactly that point. It's arbitrary because it won't affect your loss at all, right? Anywhere in that region would be the same loss. One other nice thing about this, by the way, is that we don't need to normalize data at all here. So all that work we did, all the annoyance, right, of normalizing features, making sure they all have the same ranges that we have to do for linear regression, that all is not needed here because all that matters is the relative ordering of the features, not the actual numerical value. Because all we're doing is splitting, right? So I could scale these things by 1,000,000 in one dimension, and it wouldn't actually affect the algorithm at all. Because all that matters is the information gain, which depends only on the labels of these things, not on their actual numerical value. The only way the numerical value factors in at all is in the sorting. So all that matters is the order. This is actually, I believe, frankly, that this is one of the reasons why they are so popular in things like boosting, is that you don't have to worry about data normalization. And so it's very easy just to run these things, again, with a more, trees by themselves are not that powerful. We'll talk about boosting in a second. But it's very easy to run these things kind of very quickly on data sets without worrying about pre-processing the data. I think it's actually one of the big benefits of trees, especially when you combine them with more powerful, from a performance standpoint, especially when you combine them with more powerful algorithms. Okay, so let's very quickly have a poll on this and ask about just some facts that you might imagine about decision trees. So the questions here are which things are true about decision trees, and then this is a multiple, more than one thing can be right here. The answers here are, let me just bring up Piazza, I had to close it, it looks like. The answers here are, once a feature is selected as a split, it will never be selected again in the tree, anywhere lower down. Number 2 is if it's selected as a split in one level, it will not be selected as a split in the next level immediately down. 3 is assuming no training points are identical, they can always attain 0 error if they train deep enough. And 4 says the loss will never increase after a split. So which of these are true about decision tree training? Let me open up the poll. Okay, so so about 50-50 on this last one. Most people thought this could happen. You could select the feature again. Most people thought this wouldn't happen, and then this was sort of in the middle too. Okay, so anyone want to talk about any of that? Actually, let's talk about the first one. Who wants to have an opinion on the first one? Why can you or can't you select the same feature twice in the tree? You can describe it either kind of graphically or just in some sort of intuition, or just in terms of your basic intuition about what would happen here. Yeah. Yes. Yep. Yeah. That's exactly right. So yes, this one actually can be selected twice, right? Because you could have, if I split it once on this, if I split once this way, say, in my data, in this region now, actually this is a bad example because I'm just gonna do the same thing. But certainly let's put one like here or something like that. Let's put one like that, right? So if I go in this region, maybe do like this too. If I can, actually finding it hard to find the exact example that works here. But basically, if I want to kind of carve out, this point here, after I've done this main split here, I have to, break again on this coordinate at least once, right? Maybe here I'll break again and say everything on this side is one, and everything on here is another one, or at some later point do that, right? So the point is that in order to sort of do these breakdowns, you certainly can, you could and will want to split more than one time on each coordinate. Now, as people sort of rightly said, and I'll just sort of say this too, it is true that you'll never do it right after the other. So one is not true, I guess. So saying it will never happen again. It can be selected again, but two is true, right? Because if you were to select the same feature immediately afterwards, that means you're someone picking a different breakpoint, so you should just pick the first breakpoint to begin with, right? Actually, it wouldn't be that valuable to do that. There actually are some cases in which, like for a continuous feature, this actually could kind of work, but for the most case, this actually, I believe this actually, I mean, the intuition is not that obvious for continuous features, but this is true. Now, third, this is also true. Yeah. Yes.
Data in which we have all pluses here.
Yeah, actually, another thing about it, you're actually right. Actually, I take this back. This one actually is not true. I was thinking in the discrete case. So actually, in the continuous case, this actually can't happen. If you just think about, so I take that back. Ignore what I just said. This will not happen in the discrete case. That is the case. The first one can happen in the discrete case, because in the discrete case, even if you're always at the corners here, you can be a case where, the first time I want to split here, and then, considering only a subset that I want to split in the same spot again. So in the discrete case, you can have multiple times that split no matter what here in some sense. But the continuous case, I mean, of course, you could just have, a data set like this, right? That's just a 1D data set, and then of course, I was let me split here, but then I would split here again, right? So actually, in the continuous case, yes, I take that back. You actually can split multiple times there, but in the discrete case, you won't. In the discrete case, it would always just be, you wouldn't be gaining anything. It'd always just be the same split you had before, so you would never want to do that again. Even though the first one can happen in the discrete case or the continuous case, actually. Was there a question there? Yeah.
Why wouldn't you happen for the discrete case if you have like multiple classes and, for example, there's like one of each class that you want to like split all?
Oh, but you're still thinking of the continuous case in terms of the features. I meant discrete features. So the features, if the variable itself, xj, is discrete, you're splitting already into points, into things that have one value for it and the other value for it. So you can never split it again because they're already grouped. This entire set already has, this set already has all the things where this is equal to 0. This has all the things where this is equal to 1. So there's no point in splitting this again on xj. The features here all have xj equals 0 already.
What if it's like discrete but can be 0, 1, 2, right? You have one.
Right. So yeah. So I'm assuming that for just the discrete case, you actually don't have it such that Sorry. So for the discrete case, right, you would split on all possible values of the feature, not just on one value of the feature. Yeah. Okay. So point 3 then. Assuming the points are identical, decision trees always attain 0 error if they train deep enough. This is true also, right? Because for again, non-identical points, you can always find some set of rules that will separate them all. That's the point of not being identical, right? If they're not identical, you could separate them somehow. And so if you go deep enough, you can always carve out exactly kind of regions that sort of fit each one, right? So something like this. I'm not going to draw it there, but something like that, right? You can kind of carve out this exact space that does it, and so it's sort of okay. And the fourth one, the loss will never increase after split. People were sort of divided on that. Who thinks, so does anyone want to argue for or against this? Yeah.
Since we're taking a greedy approach, you would never go forward with a case where the loss is
Right. So this is also true. The loss will never increase after a split. And the reason is that, I mean, exactly what you said, right? We're always picking the split to minimize our loss. We know we can keep the loss the same by basically putting we could put basically nothing in this region and everything in this region. That's a bad idea, but we could do that. And so it would be a bad idea to sort of split on, there's no way. All we're gaining when we split is more representational power. We could keep the exact same hypothesis as we had up here, just H, in both those two regions, but we're choosing not to. We're choosing to actually change them, and that can only decrease the loss. It will never increase the loss. So the loss does decrease there. Okay, so let's keep going. All right, so the last thing I'll say is that for regression trees, everything pretty much works the same way here, except that instead of predicting discrete values like probabilities, instead of predicting probabilities to make predictions about discrete values, you predict real value quantities to make predictions about real value quantities. But the actual prediction of loss is the actual sort of mechanics of the tree are the same. In every region of the space, you predict the same value. So it still looks like this. You still make constant predictions in each region. Just now they are real value predictions instead of probabilities that you're predicting essentially. So what this means is that if I want to know what my best prediction is in a given region, well, I should just predict the mean of that region, right? If I'm minimizing a squared error between all the points in that region and my prediction, I should do that by predicting the mean of that region. If I were to minimize like a L1 loss, I would be predicting the median of that region, but here I'm predicting the mean of that region for a squared loss. And we suffer loss just equal to the average difference between our prediction and the point, which is also incidentally the variance of the y's in that region. All right, so let me emphasize now sort of the point that I wanted to kind of to make during this lecture, which is kind of in a sense why trees are still so, they're still so kind of, despite being very, very old methods, and I guess they also work really well with things like boosting, but trees by themselves don't work that well, compared to other machine learning algorithms at least, but they're still widely used. And I think the answer really lies in this interpretability, the nature of their interpretability. So in some sense, decision trees are kind of the canonical example of an interpretable model. So say that we kind of go down our tree and we're trying to figure out what how to classify an example, and we end up over here. So we end up predicting, positive 1. Again, I'm back to the binary case here, but we end up predicting positive 1 in this region here. So the question is, why did we predict positive 1? In some fundamental sense, right? If I were to ask my model, why did you make that prediction that you made? What would it say? Well, it would say, I can look at the conditions that were triggered along each node of this branch. And so if someone wants to say, why did I predict that way? All I say is, well, because, x1 is greater than 2, and x2 is greater than 3, and x1 is greater than 3. And by the way, of course, you can, combine those two. This is the only relevant one, right? Because this implies that one. So I can say, well, I predicted this way because x1 is greater than 3 and x2 is greater than 3. Right? And this is a very powerful sort of thing. Humans really are good at understanding, conjunctions of rules like this, right? So let's take our cancer prediction data set. If I look at a point here, maybe up here, right, and say, why did you predict positive on that point? Well, you can say something like, well, I predicted positive because the mean number of concave points, again, this is, remember, my cell here, and the mean area of the cell or the mean number of concave points was greater than, say, 0.05. That's this threshold here. And the mean area is greater than about 800 or so. So basically what that does is says, this whole region here satisfies those two conditions, and everything in that region I'm predicting to be positive. But this gives you a nice rule about why, in some sense, why the machine learning algorithm is predicting that way, which is very powerful because you don't really have this with other algorithms. So this is sort of a simple case, though, I should say, because this is a case where you can even visualize, right? So in this 2D case, it's not clear it's that much better to have this decision tree than a linear model, which would just draw a line here. But this difference becomes really stark when you have high dimensions. So remember, this is actually a 2D subset of 30 total features that are included in the original breast cancer prediction data set. If I actually generate a full tree based upon all 30 features, what happens is the tree itself ends up being quite sparse. So if I look at a point in this data, and I say, if I fit a tree to my breast cancer data set, and then I look at a specific point, and I think this wasn't maybe, not sure if it was that point or not, but it was a point in data that was classified as being positive. I can tell the model, why is this point positive, right? Why am I predicting this point positive? And because only, the positive prediction might happen only a few levels deep in the tree, it can actually say, well, I predicted positive because the maximum perimeter, one of the cells, was greater than this number, and the max number of concave points, again, I think it's like averaged by the perimeter or something like that, was bigger than this number. Now compare that, and that's actually the full tree. That is a path down the full tree that has only two comparisons it does, because you don't need to go look at all the different features in the tree. Once I've met those two criterions, actually every single one of my examples is always, in my training set, is always positive. So I can kind of truncate my search there. I don't need to go any further. Now compare this to a linear classifier, right? Where if I ask a linear classifier, why is this example positive? What it would say, in some sense, and again, anthropomorphizing them a little bit, but what it would say is that, well, this is positive because 2.142 times the mean radius plus 0.119 times the mean texture, et cetera, listing all 30 features with the different coefficients, that whole quantity is bigger than 0. And that's why I predicted positive. Okay, and that's much, much less interpretable to a human than saying I predicted positive because these two criteria were met. So the nature of these, and by the way, this is exactly what it means to be a non-axis aligned direction, right? It's some linear combination of things that are diagonal directions in that space. Those are much harder for us to understand than individual criteria on each individual coordinate of our example, and usually a really small number of these. So these two classifiers actually get the same about the same accuracy on this data set, but of course the top one is much easier for us to understand. Now I should emphasize that you can get much better performance with more complex models, right? Going beyond even linear to nonlinear classifiers. And that becomes very hard. You can trace through the actual math of why it predicted this way, right? I can look through a nonlinear classifier and say, well, this thing squared plus this thing squared times this plus this, but it gives no real intuition to us. Whereas decision trees have this nice property that we can trace down their predictions through the tree and get a set of criteria that map exactly onto why we made that prediction. Okay, so now I want to be a little philosophical here for a second, because the question of all of this, and I think a very valid question, which is very prominent in data science these days, is does this really matter? Right? And I think that's actually a deeper question than you might think. Because of course it seems like, yeah, of course it matters. This is great to have an explainable model. But why does it really matter, right? So the example people often give actually are things like medical diagnostics, where you want a model that will not only tell a doctor what the prediction is, but explain its prediction so the doctor can evaluate it to see whether it's a good prediction or not. Okay, but the sort of, and I'll give you sort of my own take on this. And I think there's actually a few sort of points and counterpoints you can make on whether this is a true thing or not. But I think the most obvious sort of initial counterpoint on this, and this is data scientist number one that I guess doesn't care about explainability or interpretability, says that look, it's all great and well to say that these predictions are good or explainable, but I would rather have a doctor that was 90% accurate in diagnosing this disease than the one that was 80% accurate in diagnosing it, that, but was explainable, could tell me why, or could say sort of why they said that. I'd rather just go with the more accurate one. That seems much better, right? And that seems like a pretty effective argument too, because everyone kind of would agree with that. Of course you want the more accurate doctor. So why do we care about explanations? Maybe, there's going to be some weird space in the time from now to sort of be having, everything be automated, but this is sort of a, a hiccup of where we're currently at mentally. We don't really need these things. Now, the response to this, which I think is actually also a very valid response, is that there are times, so this is now data science too, saying that if classifiers aren't interpretable, there are times where they make kind of foolish mistakes. And they make these mistakes because of weird idiosyncrasies in the data. And unless the model is interpretable, we're not going to be able to know those mistakes are there. So a very kind of what's become almost a famous example now was actually done by a guy here. He's now at Microsoft. He was here before, named Rich Caruana. He's working with UPMC actually, and they were doing a study on diagnosing when to discharge people from the hospital based upon, and I think it's something about their breathing. I'm going to misquote it now. I should look this up beforehand. But it's something about their breathing, about how, if basically trying to know whether they should discharge them or not. It's based upon some sort of stress level of their breathing. And they trained, a neural network, and they trained a decision tree, and the neural network got better accuracy. But what they found about their model was that it was actually choosing, and both the decision tree and the neural network were both choosing to dismiss anyone who had asthma as being low risk, which is, of course, not at all the case. Anyone with asthma in that situation is immediately high risk. But what was turning out is that people with high risk that had asthma were immediately actually admitted to the hospital without further studies. So they were kind of being left out of the data set entirely. And therefore, it was actually, or they were actually even being treated differently in a different category entirely of saying that we shouldn't hold them. We should just admit them immediately. We shouldn't hold them for observation. And so the model was making the absolute wrong prediction in that case. Okay? And again, if that was a little bit convoluted what I just described there, the point was that because of some oddity that was not obvious in how the data was collected, it turned out that which is some idiosyncrasy in the data collection process, it turned out that the model was making, a medically horrible decision for these types of patients. And there's actually a lot of articles you can read. I'm sure if you Google Rich Caruana and UPMC, you'll find the articles on this. So that seems like a big score for interpretability. But the response to this is saying look, this is really not a problem of interpretability. You found an orthogonal issue here, which is the problem of training set, testing set mismatch, right? So your training set was not actually representative of your test set. You were testing it on people with asthma, but you're never actually training on people with asthma, or the labels were wrong for people with asthma. So your real problem is not interpretability, it's actually training set, testing set mismatch. And the final sort of reply to this, I would say, is, okay, that's true. That's completely accurate. If we could fix the problem of training set, testing set mismatch, then maybe we wouldn't care about interpretability. But that is a necessary evil in some sense in a lot of real data sets. And you know what a really good way to find training set, testing set mismatches is to run an interpretable model on your data, because it will come right out and you will see these rules very apparent that are making these silly decisions, which is actually exactly how it happened, right? They found these rules because they first ran a model. So maybe it's all well and fine to sort of say, okay, we're going to, once we have a perfect data set that is truly representative of our population, then we don't care anymore about interpretability. But it's arguable whether we're really going to get there or not. And so interpretability as a tool to diagnose the problems of machine learning algorithms is actually quite powerful. So that's sort of all I'll say about that general trend. They're actually going on right now at CMU, I think starting this afternoon and tomorrow. There's actually a conference on ethics in AI, which under which rubric actually things like interpretability are very important here. So this is very much a conversation that is ongoing. And while this is kind of my take on this argument, a little bit back and forth, there are many more perspectives on this. So you should certainly, I'd encourage everyone, if there are any openings in that, to check that out and see what different people are thinking about in these topics. Okay, so before we end now, any questions on that before we move on? Yeah.
So essentially, you are asking us, like, using your method, we have to use both the techniques, like to get an interpretable result.
I mean, I don't really have a technique here that I'm advocating for. I'm just saying that I think that interpretable models, if nothing else, are objectively a useful tool to diagnose idiosyncrasies in your data set. If you run an uninterpretable model and you get 100% accuracy, why are you getting that, right? It's very hard to know why that's happening. Is it something where you're cheating in your data set? Is there some sort of thing there that's just wrong about the data? Maybe you mislabeled everything, right? I mean, it's possible, right? If nothing else, what an interpretable model can do, and I don't want to advocate for using them as their final thing, but one thing they are very good for is debugging and diagnosing problems with machine learning algorithms as a whole, even if you don't end up using them in the end. So it's very useful to run a decision tree on your data, a really shallow one, just to see, and then see what accuracy it is. If it's getting horrible accuracy, then you may have to run a deeper one. But running even a very shallow one can be very useful just for getting an understanding of what your data essentially is saying. Of course, it will not work for every problem. For image detection, stuff like that, it will not work. Right? You can't look at a single pixel and determine if it's a dog or not. But for a lot of tasks that aren't like that are more from tabular data, they can be very effective, even if they're not what you use in the end. All right, so let me now very briefly mention boosting. And actually, kind of, I should say, I'm going to describe boosting, but I'm going to do it very briefly, and mainly it's kind of as a reference you can go back to if you want to learn more or think about learning more, because I'm not really going to describe much of this in too much detail, other than to say this is actually where trees get their sort of not just power from interpretability, because we're actually going to give up interpretability here, but this is where trees actually are still very much relevant and at the forefront of the best performing models in machine learning and data science, at least in some domains. Okay, so the basic context here is decision trees have some notable advantages. They're fast to train, they're insensitive to the scale of input features, so they're both really nice things. But they also are somewhat limited in sort of their actual ultimate performance because they are constrained to this hypothesis function, which is just looking at axis-aligned hyperplanes that sort of partition the whole space, right? And so they need a separate rule kind of for each partition, and they will assign a class to each partition. And if you think about it, to cover the space of all your possible examples, you can need maybe a lot of decision trees to do that. So the basic idea of ensemble methods as a whole, and two of the most popular of these are called random forests and boosting, is that you want to combine multiple tree models together to get a better estimate of your hypothesis function or of your underlying function of your data. And these both actually are very common, random forests and boosting. Random forests are actually much simpler. You just resample your data each time, fit a new tree, and just combine all of those kind of blindly. It's maybe a little bit more complicated than that, but not that much more actually. You basically just resample with replacement your data, run a tree, and then average a bunch of those models together. Boosting's a bit more complicated. Boosting involves actually up weighting and down weighting your points as you sort of proceed through rounds. But it actually also performs a little better. So really, gradient boosting in general is one of the most, as I said, sort of legitimately probably the single state-of-the-art algorithm you would want to apply for things like tabular data. Maybe not for things like image data. There you probably want to use convolutional networks, certainly. But for things like tabular data, where you just have a small number of features, it's really hard to beat boosting. But as I also said, once you're now talking about an average, a weighted combination of 100 different trees, that interpretability is just not there anymore. I mean, people claim that there's some element of it, but it really is not. 100 trees, their scores all averaged together is not any more, to me, interpretable than a linear classifier or a convolutional network. Okay, so boosting is sort of really kind of an amazing idea how many different places this has gone in the history of machine learning. So as I said, we started with decision trees, and then along came this actually very theoretical idea in the early 90s about how to boost the performance of what were called weak classifiers. So the idea from a theory standpoint is if you have a classifier that can always do a little bit better than a random chance, can you somehow combine these to actually get a really good classifier? And the answer was yes, theoretically, but it was really just kind of a theoretical curiosity because, of course, you can't always get a classifier that's a little bit better than random chance. That's the point. If you could of course do as well as as well as anything, but you can't always do that. So after this weird sort of they emerged from this kind of theoretical area, boosting methods. Then in the 90s, there were some sort of amazing practical applications of boosting, starting with the AdaBoost algorithm, which is was one of the kind of these, and still one of the primary boosting algorithms. The other interesting thing is that after that happened, a lot of people started trying to describe different ways to interpret boosting algorithms. What was actually happening here when you run these algorithms which are combining multiple trees in certain ways. And the way that I kind of agree with the most, or at least think is the simplest way of doing it, and also which perform very well in practice, is called sort of the gradient boosting view of decision, or the gradient boosting view of boosting. So I will describe this very briefly here. It is a little bit. This is actually the most complicated part of the class, or the most complicated part of the lecture. But don't worry about the details here. If it makes sense to you, that's great. If it doesn't, that's also fine. For those that sort of want to know a little bit about how this works, I'll describe it briefly. Okay, so gradient boosting works the following way. Let's suppose we wanted to minimize this function, right, our sum of losses that we have, as we were the whole time before. But instead of thinking about, so we're going to minimize, and I'm not going to even say what we're minimizing over. Well, I guess we're minimizing over theta always, our parameters. The sum of our data set of our losses between our just kind of a generic prediction here and our actual output. This prediction can be kind of anything. If we wanted to actually adjust our predictions kind of globally in some manner, the way we should adjust them is actually just in the gradient of the predictions themselves, which is kind of weird because before we had to specify our prediction as a function of which is some hypothesis function, but here we're saying no, I'm going to let you actually change your predictions no matter how you want to improve our performance. And the way you do that, well, you would just take the gradient with respect to the actual predictions of the loss of that prediction, right? Which is actually an easier quantity. This is actually a really simple gradient. It's an easier quantity than normal gradients because you don't have to worry about parameters. I'm just going to say, look, if I could adjust my predictions arbitrarily, I just look at my errors and basically make the predictions change a little bit to go in the direction of making the errors smaller, right? So for like a squared error, that would just be basically move everything a little bit towards the actual value. So there's no actual notion even of a real hypothesis here. It's just you can predict however you want on each example. So what a gradient tree does is actually a very cool idea. It's going to compute all these things, and it's going to fit a tree, a regression tree, to these gradients. Okay, so it's going to compute, and these are called functional gradients. That's a complex name for just saying just a gradient with respect to the predictions themselves. It's going to compute these gradients and then fit a tree numerically to those gradient values. And then add that tree times a little step size to an ensemble, which is kind of like doing a gradient descent step in the space of these general predictions here, but where I can actually now, of course, generalize them because I'm actually fitting a tree to them. So I can actually also get a sense of where those predictions would be elsewhere. Okay, so here's the algorithm. I won't actually bother writing it down. Okay, so you have a data set, x and y pairs. I initialize my predictions to all be 0 at first. Right? Then I compute my gradients with respect to all my predictions. So this is actually a vector of all possible gradients for each example. The gradient with respect to that example of the prediction with respect to the loss function. I'm now going to train a regression tree. That's basically a tree that's aiming to minimize the mean squared error, given the inputs, trying to predict that gradient. So this is kind of weird, right? I'm taking a gradient and I'm fitting a tree to the gradient itself. But then I update my predictions to be my old prediction minus a small amount times the gradient. Sorry. If it was times the gradient, this would just be gradient descent on the actual predictions themselves, but minus a small amount times what my tree predicts on those gradients. So what I'm doing here is I'm forming a collection of trees that kind of simulate what gradient descent would look like on this data set. Okay, if I were able to adjust my predictions however I wanted. But then importantly, what you'll actually notice is that this whole sequence of like gradient descent steps is actually just a combination of the predictions of multiple trees. So importantly, if I'm given some new example, I can actually predict, or sorry, this should actually just be x here. This should not be an I. It has some new point x. Let me actually fix that really quickly because that actually is very confusing. Okay, there we go. So if I have some new data point x, I can essentially simulate what gradient descent would have looked like on this data set. I mean, not looking at the actual label, but just following the same procedure of what my predictions were by just summing over all my alphas of my hypotheses at every sort of time step here of kind of a gradient descent-like procedure. So this here is actually just a combination, of course, of different tree predictions. But what's very interesting here is this kind of simulates, what happens to all the other points under this gradient descent procedure. So this is sort of totally wild in some sense, right? Because we're using trees to approximate gradients. We're taking gradient descent steps in the overall space. And at the end, what we have, therefore, is a collection of trees that predicts the label or predicts the output at each point. And so we can apply this to a new data point and get a prediction on this new data point. So that's the gradient boosting algorithm. And it is kind of the most common, or one of the most common methods for boosting that's sort of used in practice. I think at this point actually is quite a bit more popular than things like AdaBoost. You actually can show that AdaBoost kind of reduces to this under certain loss functions, et cetera. But this is sort of the basic idea of the gradient boosting algorithm. Now, a little bit more kind of detailed here. So fitting the trees is slow. So it is common to do something like a line search to see like how big of a step we should take at each gradient iteration. We can also take different gradient steps at different leaves in the tree. So we can actually look at each leaf and take slightly different steps at each leaf node in the tree. So not one step on every at leaf, but actually different ones on each of the ones. And here again, for the most part, I claim, I think rightly, that most machine learning algorithms are very, very simple. Here, and actually this, you can write gradient boosting in about 100 lines of code. So it's not, scikit-learn I think has many thousands of lines. I actually don't know why, but but you can write it in 100 lines of code. They have many hundred for an SVM too. But of course, it is a little bit more hardened and all that kind of stuff. But you could write it in about 100 lines of code, a gradient boosting tree. It's not that hard actually. It's kind of a fun exercise to do if you want to take some time and do it. But I wouldn't recommend it at this point. There are enough bugs you can make that you will have to spend some time fixing those things, making sure that they're all correct. And there are enough sort of subtle design choices you can make that will affect performance. So for this, I would recommend using a library. Maybe for an SVM you do too, just because it's easier that way. But an SVM you can really write. In fact, you are writing on your homework. The actual code itself is really, really short. This one, not quite so short. Still short, but not quite so short. So for these, it's fine if you want to use libraries like XGBoost or scikit-learn. Okay, I'll actually just end with saying that. I'll just give some. You can look at this yourselves, but the point is that these things are actually quite easy to fit with scikit-learn. So decision trees themselves are actually kind of complex with in comparison to like an SVM. But fortunately, you don't have to write those either. So you can also use scikit-learn for those things, and you can use scikit-learn for things like gradient boosting classifiers as well. So, and I think the next two slides I just show sort of what these look like on our different tasks here. But that actually is all I'll say about this. So next time we're going to talk about deep learning, which is the other state-of-the-art, also very non-interpretable machine learning algorithm people are very into these days, and we'll talk about that. And we'll talk about it in the context of data science in particular.